Hello, and welcome to the sixth in the series of lectures on the Piezoresponse Force Microscopy and Spectroscopy. And in these lectures, we are going to have a quick tour through the advanced spectroscopic modes in PFM. So by now, there is a rather extensive list of the variants of the PFM spectroscopies, starting with the switching spectroscopy PFM, where the hysteresis loop is measured at each point of the sample, which gives you a three-dimensional data set. Band excitation switching spectroscopy PFM, or BEEPS, where we measure the band excitation hysteresis loop at each location. Time relaxation piezoresponse spectroscopy, where the relaxation is measured at each point in single frequency or in the band excitation mode. The non-linearity mapping, dynamic PFM, switching dynamic spectroscopy PFM, first order reversal curve PFM, and contact cKPFM. As you can see, these techniques come with the rather high dimensional data sets. So SSPFM and time relaxation give three-dimensional data sets, BE method give four-dimensional data sets, and SDS PFM, fork PFM, and cKPFM give rise to the five-dimensional data set. So in this lecture, I'm going to illustrate how these techniques developed over time, and more importantly, why they have developed. So clearly they were created for a reason, and the reason was that each of those methods was developed to target specific aspects of polarization behavior and dynamics. So let's start from the brief recap of how does the classical switching spectroscopy PFM works. So in this case, we have our PFM tip in contact with the surface. We apply the waveform, which is comprised of the switching waveform, sort of the triangular sequence of the rectangular impulses, and the measurement waveform, which can be either just sinusoidal wave or it can be band excitation wave. And what happens in this case is that once we apply the bias pulse, we create the domain below the tip. Our measurement pulse start to measure the sum of the signal from the domain and the surrounding metrics. Once we increase the bias pulse, the domain grows and the PFM signal changes. So we go up in bias and the domain grows, we go down in bias and we nucleate the domain of the opposite polarity. And basically what happens is that we use the tip to create the local bias-induced phase transition in a small region of material. And we use the measurement voltage in order to detect the formation of this domain. So ferroelectrics are great for this type of studies because the polarization switching is reversible. However, the same approach can be extended for more complex systems. And in this presentation, I'm going to illustrate several examples of this type of studies. Now, the important thing is that we don't do these measurements in a single location. In fact, we measure these hysteresis loops on the rectangular grid at each point on the sample surface. So we create a three-dimensional data set when the hysteresis loop is measured at each location. And then we can take this hysteresis loops and we can extract parameters such as imprint or the lateral shift of the loop, coercive bias, work of switching or area under the loop. And we can map this as the two-dimensional maps. And then these maps can be compared to each other or they can be compared to topography. And it tells us what is the spatial distribution of the switching behaviors inside the material. So this is the classical SSPFM. So just as a reminder, some of the references when you can read more about it, about how the data is collected and how the data is analyzed, is these papers, and some of the applications of the band excitation and DART that allow it to become quantitative are described in these publications. The question is, if we already have SSPFM, why do we even need multidimensional spectroscopies? And the answer is because the physics demand it, both the physics of the ferroelectric material and the physics of the scanning probe microscopy imaging. So from the physical perspective, we know that the ferroelectric polarization switching is hysteretic. So what does it mean? Imagine that if we are measuring the signal which is fully reversible. So for example, current versus bias on a material with a good conductive properties. In this case, no matter how we do our measurement, there is only one value of the current corresponding to the one value of the bias. So whether we are starting to do measurement from 0 and increase bias up, or we start measurement from some higher bias value and decrease the bias, or if we just somehow, doesn't matter how we come to a particular bias condition, there is a one well-defined current measurement corresponding to it. This is absolutely not the case for the first order phase transition and in particular polarization switching. So in this case, the piezo response depends on bias following the hysteresis loop, and the value of the piezo response we measure will depend whether we come to this point from below or from above. So we will end up being on the different branch of the PFM loop, which basically means that if we want to get a deeper insight in the ferroelectric materials, then we have to use more complex measurements. So we need to completely define the history, and one of the ways of doing it is through the so-called first-order reversal curve measurements. So basically what it means that if we want to study the local ferroelectric functionality, if the behavior was non-hysteretic, we would need the three-dimensional measurement. So for example, current versus bias at each spatial location. If we want to study ferroelectric functionality, the measurement needs to be four-dimensional. We need to measure something like first-order reversal curves. However, the phase transition can also be rate controlled, so it depends on whether we sweep the bias fast or slow. So if we combine these variables together, it turns out that we need to do our measurement in the five-dimensional space. So two dimensions are x and y, the spatial grid. And then we want to do measurements as a function of stimulus, as a function of history, and a function of time. So it's really complicated. Second is the scanning probe microscopy perspective. So in order to do quantitative measurements in SPM and decouple topographic and functional signal, we need to use something like band excitation, which basically adds one additional dimension. So it turns out that if we want to be in a physically very well-defined system, we have to run a six-dimensional measurement. So obviously, it's not plausible to do that all the time. So very often we select the specific subset of the measurement variation. So we either probe hysteresis, or we probe the time dynamics, or we probe some specific form of polarization switching. So in the general case, the measurement should be six-dimensional. However, we often can impose specific restraints on physics, the phenomena that we want to study, and that allows us to study the low-dimensional functionality. So we do the high-dimensional advanced SPM spectroscopies because they are required, not because it's a lot of fun. And to be fair, it's also a lot of fun, but that's a different story. So let's start from the scanning probe microscopy perspective. So in the toy model of the switching spectroscopy PFM, I have shown the example of the excitation signal which is sinusoidal. However, the single frequency PFM is highly susceptible to the indirect topographic crosstalk, which basically measures interaction between the variation of the local topography and makes the measurements somewhat unreliable. So one way to improve it is to substitute the sinusoidal excitation by the band excitation signal, which gives rise to four-dimensional band excitation switching spectroscopy PFM, or to make it less of a mouthful, we just call it BIPS. So this is how the BIPS measurement work. We have our classical switching spectroscopy waveform with the write step and read step. However, at each read step, rather than measuring the single frequency signal, we send the band excitation waveform and we detect the response at this band of frequencies. So all of a sudden, our measurements become four-dimensional, so we start to probe both the evolution of material response and the frequency dependence of the cantilever response. And we get this four-dimensional data set, which can be separated into the behavior of the amplitude at the resonance. So this is the maximum of the signal. It also tells us the evolution of the resonant frequency and the evolution of the dissipation. And that's actually really interesting because the evolution of resonant frequency and the dissipation tells us something about the nature of the tip-induced polarization switching. So are the elastic properties of the material changing during the switching process? And I'll show you a few examples of that. Now, the interesting thing is that implementation of BIPs immediately brings us in the so-called big data area. So the typical size of the four-dimensional BIPs dataset is about 300 megabytes to 1 gigabyte, and we can really acquire it in 1 hour. If we start to measure the five-dimensional datasets, for example, for Piezo or kinetic measurements, it actually brings us into the medium gigabyte range, and the acquisition times is about 12 hours. So it's fully doable, but we need to learn how to work with the large volumes of data. Now, let me show you a few examples of BIPs being very, very useful. So this is the example of the ferroelectric sponge created by Dr. Martin McLachlan at the Imperial College. So basically, this is a very friable network of the PZT rods, which form essentially this solid foam. And if we look at it in more detail, you can see that these are really small ferroelectric structures. And obviously, this system is very topographically inhomogeneous. We just have these huge holes between the pieces of the ferroelectric material. So it turns out that once we have the band excitation Piezoresponse Force Microscopy, we can measure the switching behavior even in this type of material. So if we do the BIPs dataset over the rectangular grid, you can see that if our tip is on the solid part of the object, we have very good switching behavior. So it is common to represent the BIPs dataset as a 2D spectrogram, where the horizontal axis is actually time and the bias goes up and down like this. And the vertical axis is frequency. So if the signal is straight line, that means that the resonance frequency does not depend on bias. And if the signal is like this, that means that the resonance frequency actually does change over with the bias. And in this case, you can see that we have very good response over the solid chunk of the material. We have a significant variability of the resonant frequency because of this scanning instabilities over nominally empty spaces. But overall, we can actually map the switching behavior in these structures, and you can see that the holes don't switch very well as can be expected, and the material is actually switching and forms a nice hysteresis slope. But the nice thing about this BIPs technique is that it allowed us to perform polarization switching studies in extremely topographically non-uniform system. So we basically can work on extremely adversarial conditions. However, it allows us to go further than that, because in addition to measuring the electromechanical response, it allows us to map the changes in elastic properties of the material during switching. Why does it matter? It matters because in the field of ferroelectrics there are several techniques, such as ultrasound spectroscopy or resonant ultrasound spectroscopy, which detect the small elastic deformations, for example, due to the phase transition polar nanoregions and twill walls. And these mechanical inhomogeneities or mechanical changes affect the macroscopic acoustic properties of the material, and that can be measured rather precisely. So it turns out that we can do the same type of measurements in the BIPs and use the frequency channel to get insight into the switching phenomena. This is the example of the polarization switching in the PMN-PT single crystal, when we measure the hysteresis loop and we explore how the loops behave. We find out that the loops are highly unusual, so unlike the normal materials, in some places the loops are well behaved, and in other places the hysteresis loops show this very pronounced corners. So we don't really understand why does it happen. So in order to get some insight from the theory side, so basically explore what we have to be looking at, we looked at the phase diagram for the PMN-PT system, which has the cubic phase at high temperatures, rhombohedral phase and tetragonal phase, and then something interesting happens on the boundary between the rhombohedral and the tetragonal phase. We analyzed the free energy surface as a function of the electric field, And one thing that we know as the result of this analysis is that we expect the mechanical properties of the elastic compliances to change once we cross from the rhombohedral phase to the tetragonal phase. So this type of elastic property changes can be understood simply because the symmetry of the material changes, so the tensor of the compliance matrix should change. However, the thermodynamic theory tells us how significant do we expect this change to be, and it turns out that it actually can be considerable, so it can be several tens of the percent. We can get the same insight in the process from the phase field modeling. So if we model the material to be contain the charge and bond disorder, we can analyze the average polarization as a function of the electric field and come to the conclusion that application of the voltage should stabilize the tetragonal phase. So that's fully expected, even from the simple thermodynamic viewpoint. The reason why it matters is that we expect the tetragonal phase and rhombohedral phase have different elastic properties. Therefore, if we look at our data and we look at this strange hysteresis loop which have these unusual features, and we compare this hysteresis loop with the resonance frequency hysteresis loop, we can see that the resonance frequency also shows the hysteresis. And what it means is that once we perform the polarization switching, the polarization of this material doesn't just flip from up and down while maintaining the elastic properties invariant. In fact, the polarization in this case rotates, and this rotation results in the softening of material in the course of switching process. So we conclude that in this case, we have the local tip-induced transition, which is associated with the polarization rotation below the tip. This rotation softens the material, and we can detect it through the resonant frequency signal, basically acoustic signal. And also, this rotation is associated with the enhancement of the response due to the motion of the phase boundary. In other words, this elastic signal can be extremely useful. This type of dynamics is observed in different materials as well. So this is the example of the polarization switching in the bismuth ferrite when we actually perform the switching with the progressively increased triangular pulses. So we start with a small one, and then we go to the yellow one, which opens up more, and then the green one that opens up even more, and so on. And we compare the behavior of the 2D spectrogram for the off field and on field. So look at this data one more time. So in this case, the horizontal axis is time. The voltage during this time is changed according this zigzag curve. So first order reversal curve. We measure using the band excitation the response versus frequency. So the vertical is the frequency axis, and we do it during the off state and during the on state. So when bias is off and bias is on. If we take the measurements during the off states and represent them as 2D spectrogram, you can see that the material switches, but the resonant frequency stays roughly the same, which means that our material comes to the same elastic state. However, during the on state, you can see that we start to develop a very complex pattern. So in the high bias, material becomes softer, the resonant frequency decreases, and the higher is the bias amplitude, the more complex this behavior becomes. So first it softens a little bit, then it softens a lot, then it starts to develop the fine structure, sort of it softens to saturate. So we can take this data and we can plot it as the hysteresis loops for the resonant frequency and the Q factor during the on-field and the off-field state. And you can clearly see that on-field state nothing changes, but of the off-field state our frequency goes down, so material becomes softer. And also we find out that our Q factor goes down. And if the Q factor goes down, it means that the losses in the material go up. So we have some interesting dynamic process in the material that results in the softening and increase of the lossiness of the material during the bias on state. And further details of this work are summarized in the So you can read about the BIPs and its application in these references. And now we can go for slightly different modality for the PFM measurements, which is the probing of the time relaxation. And this is the example of the measuring the time relaxation in the PVDF, the polyvinylidene difluoride polymer. So in this case, the measurement is performed very similar to SSPFM, but instead of measuring the response as the function of voltage, we measure the response as the function of time. So in this case, we apply a bias pulse, and then we measure the response as the function of time during the application of the bias and after the application of the bias. So in this case, this was more than 10 years ago. So in this case, we did the measurement with just the sinusoidal signal. And we measure the relaxation at each point, and then we'll fit it by the suitable functions, something like exponent. And then we'll get a maps of the remanent amplitude. So remanent amplitude is what is the polarization after the relaxation, of the relaxing amplitude, so what is the relative change of the polarization during relaxation, and the relaxation time, so how long did it take the polarization to relax. And in this case, you can see that the data is relatively high noise, but you can see that we can measure the distribution of relaxation time within the single 200 nanometer nanoparticles. And interestingly enough, it's almost. So the additional details of these studies for the ferroelectric polymer and more complex cases of the ferroelectric relaxers are given in this application. What other dynamic modes of PFM are available? So it turns out that we can use the PFM to study the ferroelectric nonlinearity. So what we do in this case is we measure the PFM signal as the function of the magnitude of the band excitation signal. So we probe the response simultaneously in the frequency domain in order to make sure that there are no changes in the dynamic behavior of the cantilever, and we probe the signal as a function of voltage. For a normal linear piezoelectric, we expect that the amplitude of the signal is going to change linearly with the voltage, so just definition of the linear material. However, in ferroelectric materials, the response can be a nonlinear function of the driving voltage. And in this particular case, if you look at this data, you can see that there is a slight shift, slight trend of the data to be superlinear. So it goes almost like with signal with some contribution of the quadratic component. So we can do this measurement several times, so in this case 25 times, and we can compare the piezoelectric constant, and we can measure the alpha. So alpha in this case is basically the coefficient between the quadratic term. So this data is fitted by the parabolic function, and the alpha v square coefficient is plotted here. Interestingly enough, we get the value of the alpha, which is stationary, so the measurements are reproducible. And what was also interesting is that the alpha over d33 is the parameter which turned out to be very close to the macroscopic. As usual, in the advanced PFM spectroscopies, we can do these measurements as a function of position. So to do that, we fix our tip at one location and measure the nonlinearity and map this alpha over d33. We do this measurement in the second location, and then we can get a spatially resolved map of the ferroelectric nonlinearity inside of the material. And the very interesting thing is that in this case, we compared the nonlinearity determined from global measurements. So this is the red dots are the measurements obtained from macroscopic measurements on capacitors, and the blue dots are the data derived from the scanning probe microscopy. You can see that these data points fall on exactly the same curve. So we expect it in this case because by the nature of the measurement process, we expect the signal to be exactly the same units. However, once we do these measurements in a scanning probe microscope, we have this additional advantage of the spatially resolved mapping. And the very surprising result was that in the thick film, the nonlinearity is uniform and high. In the thin film, the nonlinearity is uniform and low. But in the intermediate thickness of the film, the nonlinearity appears in the form of the clusters having the high nonlinear response in the matrix having the low nonlinear response. We don't know exactly why that happens, but we do know that these clusters are much higher than the grains in the material. So each of those clusters contains hundreds of the ferroelectric grains. So this seems to be a signature of the collective response in the ferroelectric thin film. And that's really important because if we want to understand these materials and improve their functionality, understanding what is the length scale at which the ferroelectric nonlinearity forms is actually quite instrumental. And being able to resolve it is, of course, rather important. So these studies on the nonlinear mapping are summarized in this series of papers, primarily done in collaboration with the Susan Troyer McKinstry group at Penn State. Now, what about the dynamics? So I mentioned in the beginning that dynamic of the phase transition can be pretty important, and probing dynamic in the hysteretic systems is really not simple. So let's look at the following example. So imagine the system with a single ground state. Basically, that means that no matter where we start initially, the system with time will evolve towards the single ground state. If we do measurements at sufficiently high times, then there is no hysteresis, so we look at this blue curve. If we do measurements at the sufficiently short times, then we'll have a sort of kinetic hysteresis like this red curve over here. Now, if the system is ferroelectric, it's bistable or have more than two long-term stable ground states, the behavior can be totally different. So we expect that for the quasi-static hysteresis loop, we have an almost ideal shape. But for the fast measurement, we start to see this sort of smearing out of this hysteresis loop. And it's reasonably difficult to understand and analyze this behavior even on the semi-qualitative level. However, the question is, maybe it is difficult to understand, but first of all, can we measure this type of spectrogram as shown here? And once we get the spectrogram, we represent it as the time-dependent hysteresis loop. So if you look at this data, the way you read it is this is a classical hysteresis loop, but these hysteresis loops are plotted as the function of time delay. So the blue loop corresponds to the measurements done immediately after the application of the bias pulse. And the red loop corresponds to the measurements done quarter a second after the application of the bias pulse. So if the blue curve, red curve, and all the intermediate curves coincide, it means that there is no time dispersion. So for this particular bias, the response doesn't change as the function of time. If you start to see that there is a difference between the blue curve and red curve, that means that there is a time dispersion, the signal changes. And in this case, you can see that for different locations, we have different hysteresis loops. So in location 1, it doesn't look like anything normal, but that said, this is a ferroelastic material with a complex domain structure. We don't expect it to show normal square hysteresis loops. In the location 3, where we did the measurement of the top of the out of plane C domain, we see the classical hysteresis loop with the large nose, and you can see that in the central part of the loop there is no time dispersion, but the nose shows very significant time dispersion, so it opens up as the function of time. And in location 2 we kind of have an intermediate case. Question becomes, what are you going to do with this data? So once we go from the 2D spectrogram to this type of representation, we still have a 4-dimensional data set. So the question is, how do we visualize it and how do we learn what really happens inside the material. So one of the ways to represent this data set is to represent the domains of relaxation. So in this case, we plot the signal in the three-dimensional coordinate system where this is x, y, and the vertical axis is voltage. And if there is a time dispersion, we put a shaded region. And if there is no time dispersion, that we show the transparent region. So this approach allows us to visualize the regions which have time dynamics, typically at high voltages, versus the regions that don't have any time dynamics. And of course, we can also make cross sections laterally through this three-dimensional object. Another way to work with this data set is to perform the functional fit on each time step. So basically, we have our response versus time. In this case, I show only the amplitude. And then at each time step, I perform the fit by the exponential function. So in each segment of the PFM dataset, I find the equivalent representation in terms of the offset, relaxation amplitude, and the relaxation time. So in some sense, it's the extension of the relaxation PFM to arbitrary voltage and multiple locations. And then I can take any kind of cross-section. For example, this is how the offset at 5 volts look like, and this is how the offset at the 6.2 volts look like. I can also represent this data in the form of the hysteresis loops, but now I can separate my 5-dimensional data set in several 2-dimensional representations. So for example, I can have a hysteresis loops for the offset, and interestingly enough, it doesn't show the hysteresis, so the offsets are non-hysteretic. I can show the hysteresis loop for the relaxation time, and I can show the hysteresis loop for the remnant signal. And you can see that this contribution is not hysteretic and this contribution is hysteretic. I can also get the spatially resolved map of the relaxation parameters, so the amplitude or relaxation time or the relaxation amplitude, and that gives me some information about what happens in the system. Again, without being able to correlate this data directly to the structure, it is perhaps less useful than it could be otherwise. But nonetheless, we know that we can do the measurements, we can represent them in the 3 and 2-dimensional spaces, and we know that these measurements are reproducible in high veracity. So once we learn how to correlate these studies with the local structure, for example, by focused X-ray or micro-Raman or other techniques, this will get us much bigger insight in the internal dynamic of ferroelectric material. So you can read more about the dynamic PFM in these 2 publications. Now, what about switching in time and voltage domains? So as advertised, most of the dynamic PFM modes were derived to explore the specific aspect of the physics of polarization switching. The same is also the case for the SDS PFM. And in this case, the inspiration came from the classical approach for probe switching dynamics in the macroscopic materials, which is illustrated here. So imagine that we switch our ferroelectric by the sequence of the voltage pulses. So first we use a positive voltage pulse, which is done in order to establish a fully switched positive polarization state. Then we apply the second pulse, which is used to make a correction for the non-switching polarization, like in PAND algorithm. Then we perform the switching in the opposite direction by the pulse where we vary the magnitude and timing. And then we use a third vertical pulse in order to perform to get the information of the measure of switch polarization. So basically these pulses are used to set the system. This pulse is used to detect the polarization state, and this pulse is used to explore the switching as a function of time and voltage. Then the data obtained in these measurements is represented as the fraction of switch polarization as a function of the voltage magnitude and switching pulse. So it turns out that if our switching pulse is very large, then polarization switches instantly. If our voltage pulse is small, then polarization doesn't switch for short pulses and then it starts to switch. And then for the intermediate pulses, we start to kind of map the switching kinetics. So this is a very well-known approach for probing polarization dynamics. And there are theoretical models that are used to explore this type of behavior. So once there is a data, you can fit it for a specific function, and this function is connected to the stochastic switching mechanism. However, these measurements lack spatially resolved information. So once we have switching, we really don't know where it happens. We only know what is the average behavior. Also, there is a small problem that any current measurement is also limited in terms how small an object we can explore. There is a limit to the current detection by the. So can we use the same approach for exploring the polarization switching behavior in PFM? And the answer is definitely yes. So this is the example of the nanoscale ferroelectric capacitors. So they're formed by putting the gold and copper electrodes on top of the PZT, which was grown on the strontium ruthenate and strontium titanate. So these are rather beautiful capacitor structures. This is how the PFM signal looks on them. And this is how the hysteresis loops measured by SSPFM look like. And what you can notice is that this hysteresis loop are almost perfectly square. So it switches from -2 to 2 volts. These are perfectly square hysteresis loops. And the switching is really, dynamics is really hidden in the very narrow interval of something like 1 to 100 millivolts. So to get the insight in the polarization switching in these materials, we implemented this local analog of the macroscopic switching dynamic measurements. So of course since in PFM we rely on the strain detection as opposed to the current detection, we need to modify our measurement protocol, and this is what we end up having. So we have a waveform that has a set pulse. So the set pulse sets the material to the uniform polarization state. Then we probe the polarization state by the sine wave or band excitation wave. Then we apply the switching pulse where we vary the width and voltage. So this is our sampling parameters. Then we measure the polarization state again, and then we again apply the set pulse. And then on the second repetition, we, for example, increase the width of our pulse. So the total waveform looks like this. So you can see that there is a sequence of pulses of different time widths, but the same magnitude, 1.9 volts. This is the same sequence, but the magnitude is now 2 volts, and this is the next sequence where the magnitude is now 2.1 volt, and so on and so forth. So basically in this case we vary both the time and the magnitude of the switching pulse. And this is how our results look like. So this is a typical progression of the switching process within one capacitor. So the capacitor is given by this green contour at the fixed bias amplitude as a function of time. So in the beginning of the time, the capacitor is all negative. Then we start to create a switch region here. Then this switch region grows. Then we start to create the switching region here as well, and this domain keep growing, and then the whole capacitor switches. So this is one cross section corresponding to the fixed bias amplitude, and then we repeat the process many times for different bias amplitude. Question is, how are we going to analyze this data set? So traditionally it is done using the Kolmogorov-Avrami-Ishibashi model, where there are well-defined values for the volume fraction, switching time, and geometric dimension of the wall motion. And in principle, in this particular case, we can also do this analysis. We can get the data from scanning probe microscopy experiment and analyze it by the same model and get the behavior for the switching time versus electric field and so on and so forth. The problem is that in this case, we can use this model because this is a phenomenological function that can basically fit any data, but we don't really expect the model to be applicable because in this case, the behavior is measured locally, not. Nonetheless, it works, and we also can map the spatial variability of these parameters, and we can also show that the data upon proper scaling falls on the same universal curve. So interestingly enough, the chi behavior, Kolmogorov-Avrami-Eshibashi behavior, it holds on the transition to the nanoscale. So by itself, it's a very interesting result. And the fact that we can measure the spatial variability of this behavior is, in some sense, even more interesting. Now, what else can we learn? So is there any advantage on transition to local measurement? And the answer is yes, it is. So for example, we can explore whether the switching pathway in the material is history dependent. So what I mean by that is look at this diagram, which shows the fraction of the switched material as a function of the pulse width and the pulse voltage. So if we're here, so our pulse voltage is small and our pulse width is small, none of the material switches. If we're here, meaning the pulse voltage is large and the pulse width is large, everything switched. So the contours on this diagram, so for example, the contour corresponding to the teal color, corresponds to the same average fraction of switched material. However, the same fraction is achieved under different conditions. So in this particular case, we have the same fraction, but for short and high amplitude pulses. Here, we have the same fraction for long and lower amplitude fraction. So the question is, if the average fraction of the switch domains is the same, would the local domain configurations be the same or different? In other words, if the average states coincide, are the microscopic states the same? And it turns out that since we have the spatially resolved data, we can very easily check it. We can calculate the correlation maps along these contours, and this correlation map tells us whether the microscopic configurations are the same. And the answer is actually they are. So it turns out that the microscopic states corresponding to the same macroscopic states are almost the same, which basically tells us that the system has a well-defined return point memory, and that also means that we can represent the domain evolution through this universal wall dynamic using the level set method. So we basically have the evolution. We can take our voltage and time as one combined axis and represent the evolution of the domain as the function of voltage and time as a three-dimensional contour. And from this, we can get the velocity maps, we can get the orientation maps, and get basically the full description of the domain dynamics in these systems. So very interesting. Now, what about more complex measurements? So first order. So why are we interested in the fork measurements? And the answer is very simple, that, as I said before, the hysteresis cannot be described by one curve. If we want to describe the hysteresis, we need to explore the history of the process. And it turns out that there is one case where the history of the material can be fully described through so-called Piezoresponse model. So what the Piezoresponse model says is that the material properties can be represented by the collection of the units called hysterons. So each hysteron has a perfectly square hysteresis loop, and it has the higher and lower switching bias. Essentially, these are corrosive biases. And then the switching properties of the material can be represented as the certain density of these Piezoresponse elements. And for any given, if we have this Piezoresponse description, then for any given field history, we can represent our response through the proper integration along the path in the Piezoresponse plane. Now, the important thing is that of all the ways to represent the hysteresis behavior in real material, Piezoresponse model is the simplest. And of course, not all materials follow the Piezoresponse behavior, so we need to prove that. However, it forms a good zero-order approximation. And the question is, can we do these measurements using the Piezoresponse Force Microscopy? The answer is yes. So this is the example of this normal
switching spectroscopy PFM on the ferroelectric capacitor. So in this case, we get a pretty large map comprising 144 by 144 hysteresis loops that we can analyze to get some insight of the switching behavior. So we do the measurements at the function of the hysteresis loop window. So we do measurements for the 3-volt window, 6-volt window, 9-volt window, and so on. And in this case, we compare the global measurements, so this is the capacitor polarization bias measurements, to the average local measurement. This is a piezoresponse versus bias. So the microscopic loops in this case are actually calculated from the Piezoresponse density, because we know from the microscopic perspective the material follows the Piezoresponse model, and we also can establish the parameters of the Piezoresponse model. And it turns out that for a capacitor, the overall loop evolution and in local and global measurements is virtually identical. The only difference is this vertical offset, but in this particular case we were able to trace it to the bimorph mode, so the whole wafer bending rather than frozen polarization layer. And then of course we now start to get insight into the spatial variability of the switching behavior. So for example, we can make the maps of the switchable polarization with the bias window and see how it evolves. So you see that there is a kind of highly heterogeneous system, and in order to get the insight in the behavior, we can get the histograms of the remnant response, they're stable. We can get the histograms of the switchable response. The higher bias window, the more it is. And we can get the spatial variability of the switching behavior, which tells us what happens inside the material. So this is further illustrated here when we plot the roughness of the switching spectroscopy maps as a function of the scale. And basically the scale dependent roughness tells us at which length scale the system becomes self-averaging. And it turns out that it happens on the length scale of about 1 to 2 microns, which means that the property, which is much larger than the grain size. So it basically tells us that the polarization switching in polycrystalline material is the collective phenomenon, and the grains respond as collective clusters of pretty large size. So very similar conclusion to the non-linearity study. We can study this material by the fork PFM when we measure these multiple hysteresis loops and sort of visualize the behavior of the components in the vicinity of the crack. And in this case, we use the principal component analysis to highlight the spatial variability of the responses. Of course, this being a complex system, we don't necessarily know what exactly goes on here beyond the general statements that this is a stress relaxation in the vicinity of the crack. But it's nice to know that we can study this system, and this is one more of those areas that are open for exploring. Now, perhaps one of the most beautiful examples of the fork PFM measurements that we've seen is the mapping on the heterostructure in the lithium niobate when we have a region where lithium was exchanged to protons. So this is a paraelectric region, but it has a high ionic mobility, so it still gives us hysteresis loops. And this is the region where we still have lithium niobate, but the thickness of the lithium niobate layer is different. So here lithium niobate is thinnest, and here lithium niobate is actually pretty thick. What's interesting is that if we measure the fork PFM dataset in this case, you can see that over the blue region, we start to see this kind of narrow slim hysteresis loop corresponding to the electrochemical process. For the ferroelectric region, we see that the hysteresis loop has actually a complex shape, but it looks like it's a sum of the thin loop and some kind of addition. And it turns out that if we trace the evolution of the signal across the boundary, we see that the derivative for the forward branch is the same. Derivative for the reverse branch developed this fine structure. And in this case, application of the principal component analysis actually shows us that the signal can be separated in 3 components. So one component which is pure the hydrogen exchange lithium niobate,
second component, which is purely the normal ferroelectric, and then we have a transitional component which accounts for the interplay between the two and thickness variation of the signal. So it is very unusual for the simple statistical analysis to give this such a deep level of insight in the physics of switching process. So typically it requires much more time and effort, but sometimes things work. So you can find more details about the Piezoresponse measurements and fork measurements in capacitors in the applications. And finally, I want to briefly talk about the currently very rapidly developing variety of PFM, namely the contact cKPFM. So contrary to the name, which is a little bit not misopportune because it makes an illusion that this is just a Kelvin probe microscopy, contact cKPFM is a very complex version of the PFM spectroscopy, specifically designed to decouple the electrostatic and electromechanical effects. So the need for cKPFM has appeared in the context of the PFM measurements of the non-ferroelectric materials. So for many materials, we found that the hysteresis loops can be observed even if the material is nominally non-ferroelectric. And the reason why the hysteresis loop can be obtained is because of the surface charging. So if our tip ejects charges in the surface, these charges result in the capacitive interaction between this tip and the surface. The strength of this interaction depends on the amount of the injected charge, and the amount of the injected charge depends on the tip bias, which basically gives us the hysteresis phenomena, almost indistinguishable from the ferroelectric hysteresis. So the question was, can we separate these two mechanisms? And the answer is that yes, we can, if we configure our microscope to do the special type of spectroscopic measurement. So in this case, we measure normal PFM hysteresis loop. However, we vary the detection signal. So normally, when I showed you PFM spectroscopies, we were always doing measurement either in on state or off state, and the off state was 0. So in this case, we actually vary the off state. We can vary it from, say, negative to less negative to 0 to positive to strongly positive. And what it allows us to do is to separate the electromechanical and the electrostatic contributions to the signal. So look at this formula. The PFM response in general is the effective piezoelectric coefficient, which is determined by the domain structure inside the material, plus some constant proportional to the potential difference between the tip and the surface, multiplied by the capacitance gradient. So if we perform the measurements at the 0 bias state and go up and down in bias and measure the PFM signal, that tells us some sum of this D effective and the C prime times V tip minus V surface. However, if we start to vary the readout bias, we get some information about the slope of the response versus bias curve. So in other words, at each point of the hysteresis loop, so the point of the hysteresis loop is determined by the polarization state inside the material, we also collect the information about the electrostatic response of the surface. So the cKPFM measurement gives us this two-dimensional band of the response versus the read voltage. This band, if we take the vertical cross-section, this will give us the normal PFM hysteresis loop. But if we take this cross-section along the V-read axis, this would be the dependence of the contact potential on the read bias. So this would be the charge induction signal. Let's see how it works. Let's take three materials, the PZT on LSMO, strontium titanate on NGO, and strontium titanate on DSO. This material is a very good ferroelectric, so we know that. These materials, we really don't know whether they are good ferroelectrics or not. However, in all three cases, if we measure the classical PFM amplitude and phase loops, we see a very nice hysteresis. So they behave as if they're ferroelectric. If we measure the relaxation of the signal, we can see that in the DSO the relaxation is strongest. Actually, in NGO the relaxation is strongest. But even in the PZT on the LSMO there is some relaxation. So we cannot really look at this data and say that this material is ferroelectric and this material is not. However, if we measure the cKPFM dataset, we see a fundamentally different picture. So for the PZT on the LSMO, we see a beautiful hysteresis loop and we see two bands here. For the STO on the DSO, we see that there is a single band and there is no ferroelectric switching, there is just a surface charging. And the STO on the NGO, it's an intermediate case, so it kind of tries to be ferroelectric, but not really. So basically what we do in this case is that we learn how to distinguish the true polarization in the material, which switches as a long-range dipole, versus the surface charges and surface dipole, which switch continuously, forming one continuous band. So this cKPFM turns out to be the method to separate ferroelectric and ferroelectric-like phenomena. This is another example of the barium titanate film grown on strontium titanate on silicon with the different thicknesses. So this is data for 10 monolayer, 8 monolayer, 5 monolayer, and 4 monolayer film. So as you can see, the 10 monolayer film shows a nice hysteresis, and in fact even 4 monolayer film shows a nice hysteresis. So you would conclude that the material is ferroelectric. However, the pure strontium titanate on silicon shows a hysteresis loop, and even pure silicon substrate, of course it's oxidized, also shows a hysteresis loop. So arguably the hysteresis loop for STO and silicon are more ugly or more irregular than the barium titanate, but it's kind of difficult to make a boundary between the two. We cannot really say when the ferroelectric behavior is over and the non-ferroelectric behavior starts. However, cKPFM allows us to answer this question very easily. So the cKPFM data for the 10 monolayer film shows this very clear opening of the ferroelectric window. For 7 and 4 monolayer film it becomes more narrow, but it's still perfectly visible. But for strontium titanate and silicon we just see one band, there is no ferroelectric behavior. So it actually does work, and it proves that barium titanate is ferroelectric and strontium titanate is not, even though both of them give a classical hysteresis loop. So you can read about the cKPFM method and its application for real materials in these publications.